Good day, everyone. My name is Rebecca Lilly with the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Flexible Energy Systems, Profitable Participation of Small and Medium-Sized Industry in Future Energy Systems in Germany. We're grateful to our speakers for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speakers. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for the panelists, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated time at the end of the webinar to read and answer them. And now I would like to introduce you to our moderator and first speaker, Anas Abuzayed, Senior Researcher and Lecturer at the Institute of Sustainable Energy Systems at Offenburg University of Applied Sciences in Germany, and a doctoral candidate at Friedrich Alexander Universität. Anas, over to you.
Thank you, Rebecca. Hello, everyone. Good morning or good afternoon. So basically, the first speaker will be Nicholas Hartmann. Maybe I introduce my colleagues, then I hand over to Nicholas. So first, Professor Nicholas Hartmann is a professor of energy system analysis and energy economics at Offenburg University of Applied Sciences. His main research is or focuses on the marketing of decentralized energy markets and the focus on the German energy system with high shares of renewables. Then we'll have Amin, who's a researcher at Offenburg University as well, and his main research focus is on energy flexibility for SMEs and the modeling and optimization of the power networks. Finally, we'll end up with Jan Niklas, who's a researcher at Fraunhofer EPA in Stuttgart and a doctoral candidate, where he investigates or optimizes the models for determining the potential of flexibility in energy systems. Without further ado, Nicholas, the floor is yours.
Thanks, Anas, and welcome everybody from my side as well. I try to share the screen. And I hope everybody can see it.
Looks good.
Yes.
Okay, perfect. Just quickly need to sort. Sorry, I'm having issues now with the. All right, so welcome to the first presentation of those 4 we have. I will give a quick introduction to what we will talk about. So I will start with a general overview of the German energy system. I hope that many of you are abroad from our side, Europe, abroad in the US or worldwide. So we give a short introduction into the energy market of Germany and basically the flexibility demand. And then I hand over to Anas Abuzayed, talking about how we can tackle SMEs flexibility. He will then hand over to Amin looking at the flexibility in an industry, the digital twin of that, and a general model of that. And last but not least, you will be Jan Niklas Gerdes. You will talk about flex protocol and also prognosis within the SMEs. So we will work our way up, down from the energy system to small and medium companies to flexibility within those companies. Okay, starting with a quick view, and I want to use the time also to introduce my research group at the Offenburg University of Applied Sciences. So we are currently 8 researchers working in a very focused group. We focus on an intersectoral energy system analysis with a special focus on the industry and agricultural sector at the moment. And from technology side, we focus on flexibility within those sectors and also negative emission technologies. And we have a side topic of energy management and energy management processes. Okay, going to the energy system of Germany, I will show you some general slides, mainly from the AG Energiebilanzen AGEB, which is the source. And let's first look at the primary energy consumption, so which energy carriers we are mainly using in Germany. As worldwide, we are heavily using oil in the transportation sector. We are using gas up to roughly 24%. We are using coal and lignite. Roughly 10% of our primary energy consumption is from lignite and from coal. Nuclear is roughly 3.2% and renewables, mainly biomass, 17% primary energy consumption. And I hope you all know that last Saturday or Saturday 1 week ago, we exited our last 3 nuclear-fired power stations in Germany. So actually the real current version of today is we have a primary energy consumption without nuclear as well. Going from primary energy to final energy consumption, where is or are those energy carriers used? And Germany is dominated on the industry. Industry, put on the laser pointer in the red bar down on the right, 29% of final energy consumption happens in the industry sector. The household sector and transport sector are the medium ones, 27% roughly, so close by. And we have the tertiary sector of roughly 16%, also contributing to a large share of the final energy consumption. Okay, that a short overview on the primary and final energy consumption. Now also showing you the electricity system in Germany very quickly. So this is a graph on the left side from the energy charts, showing you the installed power of power plants over the last 20 years. What do we see? We see a decline of the nuclear-fired power station. In red, we see the lignite and coal-fired power station being quasi-constant, having a little reduction, and we have an increasing share of gas-fired power stations. Roughly 100 gigawatts, a bit less of installed power of these 3 conventional power systems. And then we add roughly 150 gigawatts of renewable energy, dominated, of course, by offshore and onshore wind, which is the light green bar here, and solar photovoltaics, which is the yellow bar on top. And aside, we have a biomass share, run-of-river, and some others. If we look at the electricity generation in Germany, we have a demand of just about 500 terawatt hours per year, gross energy demand, which constitutes out of a generation of 490 terawatt hours of renewables here on the right-hand side of that pie chart. As you see, dominated by wind energy and solar energy, you clearly see the good wind sites in Germany. Germany has not the best photovoltaic sites worldwide, of course. And on the other half of this pie chart, you see the conventionals and nuclear-fired generation, heavily dominated by lignite currently. And this is, of course, a result of the war in the Ukraine, having our gas system considerably reduced during the last 2 years to roughly 10%. Okay, so this is the installed power and the electricity generation in Germany. And I'm coming now from basically the current status to our climate goals in Germany. And I want to show that by showing you the annual emissions of CO2 equivalences, which are in this graph, and you see it for different demand sectors: the energy sector, industry, building, transport, agriculture, and waste from 1990. So we compare all our climate goals always in comparison to 1990 in Germany. And we started with 1.2 2,000 millions CO2 equivalents. Sorry, there's a millions missing. Millions tons are here it is. We declined up to date roughly to 700 million ton of CO2 equivalents. And then we set out a path to the year 2045 to reach climate neutrality in the German energy system, having clear sectoral goals for the years 2030, 2040, and even in between. So that's our future, where we are heading in Germany, reaching these climate neutrality in the year 2045. And you see also some interesting aspects here. Of course, there are some emissions which are now highlighted in the agricultural sector, which are very hard to decarbonize completely. So we are expecting to have some negative emissions, especially in the energy sector and maybe also in the industry sector, which is of course heavily to debate. Okay, so this is our path into the future, which we are trying to cope with. And then now I want to give a quick insight into our model, mainly developed by Anas Abuzayed at the Hochschule Offenburg, and what we are working on with it. So here on the right-hand side, you already see it developing. So you see it is a model of the German energy system, having a high temporal spatial resolution, and we aim at decision makers in the industry and maybe also in policy to assist in having a valid decision how to cope with our climate goals. This model was developed in a project GAIN, where this talk is about, and this was funded by the Ministry of Economics and Climate Change of the German Ministry of Economics. And it's also fully public available open source on GitHub. And what are the key aspects of this model? The model works myopically. So we start with the year 2020. We have the current status of Germany built in the model. And then we add on an annual basis, or we optimize on an annual basis, the power generation and the expansion of the whole system. And I'm just naming some highlights. Anas will a bit go into detail. Here, where are we good with this model? We are good in showing the regionality of this transition path. Yeah, we can have regional limits for certain technologies be integrated. We can have regional potentials and also overall potentials for the German energy be integrated. And we can combine it with some CO2 cap limits and also some CO2 tax limits over the years. In the end, we will work annually our way through till the year 2050, having a decarbonized system, hopefully in the year 2050. Okay, that much to the model of the German energy system. And I want to give in a few 2 to 3 minutes the basis of the transition path. Anas will also work on the industry sector. So here on the left side, you see the starting year 2020, which was the current system in the year 2020, having a high generation of lignite power plant, a high generation of coal-fired power plants, and of course, high wind, run-of-river, and solar PV generation. And in the end, this will be within the model transformed to the year 2045, fully dominated by renewables. Of course, wind onshore, wind offshore are the key technologies, including solar PV for a renewable system in Germany. If I go a bit into detail, and I just want to highlight a few aspects of this transition path. So here on the top left graph, you see the installed power in conventionals and renewable energies, which is optimized by the model in a 5-year display. Behind it is an hourly optimization of every year until the year 2050, but we show, due to simplicity, only the 5-year steps here. And on the right-hand side, you see the energy generated in terawatt hours, also for these 5-year steps. What we can see, of course, and this is an input to our model, we force it to have coal phase out until the year 2035. We have an agreement and a law in Germany phasing coal until the year 2038, but there are high chances that we get it much faster done. So there's the chance to even get out of coal in the year 2030 up to 2038. So we force the system to run out of coal in the year 2035. We also see, to compensate that, we need huge investments in solar PV, roughly the factor of 4, wind installations, roughly the factor of 5 until the year 2050. We also see in the generation chart that we are expecting an increase of electricity demand starting from roughly 500 terawatt hours to roughly 700 terawatt hours, which would be a 1% increase annually. The last thing we can also quite interestingly see, and I'm coming now to the flexibility demand, is that mainly CCGT is used. So combined cycle gas turbines are used as a main flexibility, of course, running out of the system during the year 2040 to 2045 to fully decarbonize the system. Nevertheless, until then, CCGT is heavily used just as a flexibility. So not in major generation parts, so not in terawatt hours, but in a small scale in temporal resolutions, then ramping up CCGT to add flexibility to the system. Looking at other forms of flexibility, we see in our model that there's just a huge demand of flexibility. Now, in Germany, we have roughly 7 gigawatts of installed pumped hydro storages. To cope with that renewable system, we need to ramp it until the year 2045 to 80 to 90 gigawatts of installed capacity. And interestingly, focusing mainly on long-term storages. So we have the picture of a hydrogen storage, so weekly, a bit higher storage capacity, but it is for us a long-term storage. That's the first need. The second need, then coming in the year 2035, is also some short-term storages. And in our model, actually, the short-term storages then take over the flexibility generation of CCGT, which I showed in the graph before. Yeah, short-term storages, just for everybody to have a picture behind it, would be maybe the batteries very, very short-term. No? All right, having a quick summary before I hand over to Anas is on a long-term, a system with 100% renewable energy is possible, but highly demanding and challenging. Of course, everybody knows that, hopefully. And flexibility, we see that in all our model runs, is or will become a crucial element in the rest-dominated energy system. So flexibility, who handles that correctly, is basically the winner of the future energy system. Then battery storages and hydrogen are needed on a large scale. And then very importantly, and that's why we did that model, that project, is we need to tackle all other sources for flexibility. And with that picture on the right-hand side of a future energy system, it's from the World Economic Forum, a bit old, but you see all the possibilities. And one possibility, demand-side management within industry, and especially within small and medium-sized industries, that has not been researched very much on, and that was the focus of our project. And with the climate stripes of Germany getting warmer and warmer in the last years, I want to hand over to Anas for the second part of this presentation.
Thank you, Nicholas. Before I start, just a reminder to everyone, if you have a question, just type it immediately in the Q&A session. We try to either answer it by chat, or in the last 10 to 20 minutes, we go over it in the Q&A session. So, okay. Can you see the presenter mode, or?
Yes, looks good.
Okay. So, thank you, Nicholas, for the smooth talk. Now I will go into further details how the SME flexibility was mapped into our model, what was its impact or its effect on the other flexibility measures, and the national energy transition in Germany. So maybe to start, to introduce everyone who's not familiar with the EU or with the German structure of industry. So 99% of the companies in the EU are basically SMEs, so small and medium enterprises, which employ roughly 2/3 of the people or all of the employees in the EU. And looking at Germany, that's 99.5%, a share of all the companies, and roughly 1/3 of the turnover of the whole country and 60% of the employees in the. If you look at it, comparing other EU countries, Germany would be the first to talk about SMEs with 7.6 average number of employees per company or per SME. So looking further or deeper inside the SME, we can see that the electricity prices for the companies in Germany with 52% tax is very high. And most of these costs are basically procurement or grid fees, plus the renewable surcharges. So if you look at the current status now, we have roughly 360 or 370 terawatts of electricity into the industry. But by 2050, this is expected to increase heavily. So there will be a huge electrification process in the doing, with a significant increase in efficiency and productivity. So this means there is a constant progression of the total industrial energy demand, but the energy carrier itself is changing. So we see that there is more electricity being involved into the system. So looking at the actual SMEs itself, the enterprises, the demand in there is very heterogeneous, and detailing the electrical demand is usually very difficult, very demanding, and mostly neglected. So the spatial and the temporal characteristic of these demands, especially in Germany with this vast amount of enterprises in there, would make a big difference in the energy system modeling or in the energy system analysis. However, this mapping is very different, or mapping of this different is basically needed and should be included in most of the models. So that was what we tried to do in this project. So the motivation of this work, let's say in bullet points, well, first, what is the impact of this SME flexibility on the national energy transformation goals? And on other flexibility measures, we saw what Nicholas presented, that there would be a massive demand for flexibility. Let's say conventional flexibility will no longer be valid or no longer be present in the system by the, let's say, the decarbonized future. So we need to explore other flexibilities. Another part of the motivation is how can this flexibility from SMEs participate in the network congestion management and to secure the supply of electricity? And most importantly, how can we quantify or analyze the flexibility from the demand side, or let's say from the industry? So moving to the model development, how we mapped the electrical demand from the SMEs. Just briefly, I want to show it. So we have the goal of having flexible industrial demand within our model or within our system. So we start with having a spatio-temporal disaggregation per industry type. So we have different industry types in Germany. Then we have kind of a general aspect in there. How can we proceed? So we have different regionalities. As Nicholas already mentioned, the main feature of our model is the regionality in Germany. So this is very, I would say, German specific thing, that different regions has different demands, different SME contents, different companies in them. So this is very important to map inside the model. Secondly, we have the synthetic load profiles and the industrial load profiles that need to be mapped within the model by having different processes and different times, different regions. How can these basically differ temporally inside the model. Finally, after we have the industrial load profile, we need to have the end user classification and the disaggregated load profile inside the industry. So basically, this is how it looks like inside our model, with a very high detailed level of end user classification of the processes within any industry. So you can see different processes such as mechanical or heating or HVAC or electrochemical processes. So all of these are mapped within our model that we can then assign flexibility to them by having the industrial flexibility within. So just as an illustration or as an example of our model, then we have an inelastic load within any node or within any bus within the system. And we have different flexibilities, which also differ per time, or let's say temporally and graphically, or let's say spatially. They are very different from location to location or from region to region. This is again fully automated, fully open source. Anyone can use it, and it's all based on open source libraries from other institutes that we developed over the last 3 years, so that people can also enhance it, work over it, or use it in their own research. So moving to the scenario settings of the flexibilities, we defined 3 pillars of the SME flexibility, namely the potential, the cost, and the duration. That we have different flexibility potentials from 5% to 20% only of the full load of 3 SMEs or 3 SME categories. So not all the SME sector or not all the SME companies. We only chose the food sector, the machinery sector, and very limited SME participation in this. Just wanted to kind of see a proof, does this work or not? We have different cost assumptions and different temporal settings. I think eventually Jan Nicholas will talk about them, how these potentials were triggered inside the SMEs. So we basically work together with our colleagues from Fraunhofer IPA to come up with these different settings. Inside our scenario to represent the electrification of the industry, which is expected to be massive. We have 1% increase annually in this flexibility potential. And by running a sensitivity analysis, we end up with 129 scenarios plus 1 reference scenario with no flexibility or no SME flexibility. So just to show a brief or show a proof of concept, basically this is a typical load shifting where we have extra demand at low demand periods and extra generation at other periods. Comparing 2020 to 2050, just to show how little is it, the SME flexibility that we introduced to the model. So we have 1.1 gigawatt demand side management from SMEs. This is a maximum, kind of maximum available flexibility from SMEs out of the 88.6 gigawatt load or peak load now currently in, let's say, status quo, not 2020. In 2050, we move up to 1.9 only gigawatt out of 120 gigawatt. So to establish here, we have very minimum or very minimal participation from SMEs, and we want to show, does it really affect the flexibility measures or does it affect the national energy system? Moving to the results and discussion. First, we start with the, if you look at the figure on the right, we have on the x-axis the flexibility duration from 1 hour to 8 hours. So this is basically shifting up to 1 shift or maximum of 1 shift from 1 hour to 8 hours. And the different colors represent the different flexibility potentials of the SMEs or of the full load of SMEs. We can clearly see that with less hours or less available flexibility duration, we can clearly see that even with higher potentials, it was not used. So the flexibility utilization share represents how much was actually used from the available SME flexibility. Moving up to longer duration, starting roughly from 6 hours, it nearly hits 90% as a minimum. So this means with more duration, we tend to use all of the flexibility that we need, or all of the flexibility that is available from the SMEs. So we end up with saying that basically 20% is or can be more than the system needs if only flexibility is presented as a potential. If we say looking again as, or let's say replacing or repeating what Nicholas said, with higher potential, we tend to have less other measures or less flexibility measures from hydrogen and batteries. Moving to the duration of the flexibility, basically, this means that we need more or longer term duration, longer term flexibilities, such as hydrogen facilities, and these help heavily with reducing the CO2 emissions of the country. Looking at the cost, which was the minimal effect or minimal impact on the energy system analysis on a national level, again, these are big differences in terms of millions, but when you look at the national energy system, then you move the scale up to billions. Talking about the cost of the energy transition, we can see clearly how the system behaves from 2020 to 2050 by saying, basically, we saw it in the last 2 years, or the last year, especially with the war, that the conventionals, or let's say the prices explode with the current market because it's heavily based on conventionals. Stating the clear, a sustainable energy system would require a huge amount of flexibility. Will come in the next figure what exactly is this flexibility, and stating, let's say, a renewable based or a fully dominated system by renewables is achievable. And again, it's very challenging, but it is achievable and it's much more cheaper on the longer term. Looking at the total cost flexibility, we can see that there's a huge DC grid development or huge DC expansion in Germany, moving the offshore wind from the north of Germany to the load center in the south. And the investment spike that we see when we hit the climate neutrality is due to the myopic behavior of the model, because it optimizes on a yearly basis, not with a perfect foresight. A shorter lifetime that we have. Anything invested in 15 years ago needs to be phased out in this year. So there is a potential, let's say, if the technology is being enhanced or being developed in the future, that we don't see these problems. And mostly it's because of the climate neutrality by 2045 that we need to change completely what we invested in before. Looking at the flexibility from the industry, we can see it's very minimum contribution here. So this means, again, the energy cost, or let's say the flexibility cost of industry is negligible or can be negligible. So this is something that we figured out or discovered from the analysis. And most importantly, after we hit the climate neutrality with the great amounts of flexibility from hydrogen, or let's say from long and short-term flexibility or storages, we don't really see a use for the industrial flexibility within the system. Again, this is not a solid conclusion or a solid takeout from this analysis, because as I mentioned before, it was less than 1% of the whole peak load from the industrial flexibility. To sum up my presentation, or to sum up my work, we see that the flexibility from SMEs contribute heavily to the network congestion management, so the load shedding. We see that less favored DSM settings, so less favored cost or potential, so higher cost, less potential, or less duration, increase the dependence on other flexibility measures, such as the hydrogen or the batteries. From our analysis, we saw that the flexibility from industry is usable and it can be marketable, but it will not be enough. So we need more flexibility from other participants or from other players within the system. Maybe more SMEs can come into play, or higher energy consumers. And the need to temporarily shift energy can supplement these flexibility options. And finally, with the huge electrification, this implies that there is a big and even bigger potential for demand side management to be integrated into the energy system of the future. With that, we can say that the most important finding of our analysis was that longer flexibility duration is more crucial than the flexibility potential. Normally, when we talk about flexibility, we tend to talk about the potential, but the duration duration.
So I think it's the last slide. Anyway, I would say we directly go to Amin.
Thank you.
Yeah.
So with this, I submit basically.
So thank you, Anas. Okay, so as an introduction, I will start with this illustration from Arena that shows the parts of the power system in which the energy flexibility is applicable. In this work, we focus on the demand side management, and especially for industrial consumers. As you all know, industrial companies are of significant value among all other consumers due to their enhanced contribution to managing demand of electricity, and thus offer a high potential of flexibility. So in this work, we are working on enabling the energy flexibility not only on the supply side, but also on the demand side. Leverage the high demand side flexibility potential of industrial companies as large-scale consumers, and also provide the digital flex twin as a tool to test and demonstrate the potential of industrial flexibility. So here we have the digital flex twin concept for energy flexibility. So any small and medium company can be modeled as in a modular structure. So here we have the manufacturing system, the technical building services, and the energy system. So a company can be modeled as subsystems. Sorry. So the manufacturing system is the core process of any company, industrial company, in which we define all the resources and the tasks that matter in order to produce. The other subsystem is the technical building services, which we define and we model all the media, the auxiliary services that are needed for the production, such as compressed air, the cooling system, the heating system, and so on. Both subsystems need energy, of course, and so for that we need to model the energy system in which we include all the energy assets available for the company, such as PV, wind, and so on. The three subsystems are controlled by the energy and manufacturing control, in which we define the functioning constraints and the objective function of the optimization. And also to model our company, we need external signals such as the electricity price, the weather data, and also the connection to the grid. So the optimization approach that we are using in this digital flex twin, it's a two-step optimization. We start first by the optimized manufacturing system. It's an on-loop optimization that calculate and give as an output the schedule of the production for the day ahead. And then in the second stage, we optimize the technical building services and the energy system using the model predictive control for both these subsystems, technical building services and the energy system. In our case, every 15 minutes, as we take the time step, it's each 15 minutes. So for the methodology modeling of the SMEs, first we start by creating for each use case, we create the manufacturing system of this use case. That the manufacturing system is based on the resources for this company, the machines, the products, the raw material, the storage facilities of the company, and the manufacturing tasks. So it's a resource task network of the company. And then we model the technical building services needed for the production, such as the compressed air, the process heating, process cooling, and so on. The third step is we model the energy system in which we define all the assets available for the company, such as PV, CHP units, and so on. And then we identify the energy flexibility measures. So in this step, we identify which machine, which system is flexible and which system is not. And the final step is for the optimization and the control. In this step, we define the constraints and the objective function of the optimization. So here we define all the constraints for the MFS, TBS, and ES. At the end, we get our digital twin as a consolidated presentation of the technical assets and energy flows in the SMEs. So as an outcome, we'll make it possible to check the impact of the use of flexibility before implementation. For the optimization algorithm and the objective function, once we define our digital twin, and we define all the components of digital twin, starting from the manufacturing system, and we define all the constraints and the control. The same for the technical building services and the energy system. Then we calculate the balance, the power balance of the system for each time step, which is the summation of the power for the manufacturing system and the technical building services, minus the energy assets available for the company. And then the objective function is to minimize the cost of electricity for each time step by calculating the power multiplied by the price of the electricity at this time step multiplied by the time step. Here we have the software structure of the model. So it's an objective-oriented programming structure. We start first by creating the company, the use case, and then we define for this use case its manufacturing system, its technical building services, the energy system, and the control system. And inside each subsystem, we create the machines. For example, for the manufacturing system, we create the machines that are available for this company, the products, and so on. For the technical building services, for each specific use case, if the compressed air is needed, we create a compressed air and we define how many compressors that we have, and also the air storage tanks, and so on. The same for the process cooling, the HVAC, and so on. The same for the energy system. For example, a company has a PV plant, we define their PV plant in our digital twin. So here we have a use case. It's a plastics company. We have our 3 subunits. The first one is the manufacturing system, which is composed by the raw material storage, 4 extruders of different power, 2 intermediate storages, 1 printer, and the final product storage. For the technical building services, we need only the process cooling system and the compressed air system. So for the cooling system is composed of 2 chillers that fill a central water storage tank. And for the compressed air, we have 2 compressor and one storage. For the energy system, we have PV and battery, and of course, the whole system is connected to the grid. So as a result of the simulation for this use case, so the first stage of the optimization, we get the schedule of the production for the manufacturing system. So following the variation of the electricity price, the optimizer decide when to run a machine and when not, in order to fulfill the daily production. So for example, if we go to the time step number 5, here the optimizer decide to run all the machines as the electricity price is low. And if we go to the time step 75, for example, the extruder number 3 is the only machine that is running. The same for the technical building services and the energy system. So here we have 2 prices, 2 signals of the price, in order to see the effect of change of electricity price on battery, on compressors, and on the chillers. So as you can see here, for the new price, for example, if we have the high price of the electricity, the optimizer decide to discharge the battery and so on. So we can evaluate how the optimizer is reacting to the variation of the price. Thank you for your attention.
Okay, then I'm going to start the last presentation of today. Can you see my slide?
Yes, we can.
Yes.
Perfect. All right, I'm going to try to hurry up so we can finish within the hour, but there might not be enough time for a very extended Q&A session, but I could already see in the Q&A section that Niklas and Anas have been tirelessly answering all questions. Yes, I'm going to hold the last presentation on the energy flexibility audit, which is a methodology developed here at the Fraunhofer Institute for Manufacturing, Engineering and Automatization, which tries to identify, or was developed to find a way to systematically identify energy flexibility potentials in companies. I think Anas has already introduced myself, but quickly, I'm a research engineer at the Fraunhofer IPA, and I'm also a doctoral candidate just essentially over the street at the University of Stuttgart, focusing on energy flexibility. But as you can see later, I also do a lot of work in the thermal energy sector and hydrogen integration. Today's, or the last presentation is going to be separated into 3 blocks. So I'm going to quickly give a small introduction into the topic, so a bit of a motivation. Then I'm going to present the methodology, and I'm going to illustrate some best practices. So in the earlier presentations, we have already talked about this, but Germany specifically has been or is trying to decarbonize by the year 2045. So what we will see in the coming years is a lot of building of PV, but also wind power in Germany, and this has some very big challenges which we'll need to face, which is the question of the volatility. So we can see some 2 illustrations of energy demand and supply profiles. from two different characteristic weeks. One in February, where we can see there's a lot of there's high wind power electricity production, and in April, where we can see volatile peaks from the PV or solar power energy production. And in the coming years, we are going to see even more of this volatility, not only on a seasonal, but also on a daily basis. And we'll slowly phase out the fossil demand to ensure that net stability. So we have to find other ways of ensuring that stability. And one of those ways is the utilization of demand response or industrial demand side management, which essentially enables us to adjust the electricity demand to the electricity production from the energy grid. But this does require a need for a methodology or some way of identifying this industrial energy flexibility potential, which this presentation today is about. But this also has some positive aspects for companies. So here in Stuttgart, we see energy flexibility not only as a challenge, but also an opportunity, and also as an extension to conventional energy efficiency. I've kind of qualitatively illustrated it on the right side here. So energy efficiency obviously has a lot of like a long-term time frame, but also has low economic and ecological potential. With energy flexibility, this is more on a shorter time frame specifically, which does give companies the option to to gain a lot of money and decarbonize their production systems, but it also has a big effect on the manufacturing process, which I will come back to later. So how can we achieve those goals, specifically those economic goals? So when we talk about energy flexibility, we usually talk about different goals we try to achieve. Those goals are sometimes exclude each other, but they're illustrated over here. So we can use energy flexibility to react to the volatility of energy prices, specifically negative energy prices, when we have a lot of sun or a lot of wind at the moment. But we can also use the energy flexibility to commercialize it proactively on energy flexibility markets. So we can offer the flexibility capabilities to, for instance, companies that produce electricity, so they can buy this energy flexibility to ensure the stability of their net. Another way of utilizing energy flexibility is the maximization of local energy sources. So for instance, a combined heat and power plant, but also renewable energies. So for instance, a local PV plant on the roof of the company. Some more relevant goals which are already actively pursued by conventional load management is peak shaving, which we can use energy flexibility for, and also atypical grid consumption. And a topic that has been gaining in relevance, especially in Germany, and Europe, is the question of resilience. So energy flexibility can also enable companies to reduce their electricity demand in the case of a partial blackout. Okay, I'm now going to talk about the methodology. Before we do this, Amin has already presented the systems which factories can be broken down into, but I would just like to quickly refresh on this. So when we carry out the energy flexibility audit, we typically look at 4 different systems. So we have the manufacturing systems, which are the production systems that are actually value adding to or creating the product. And we have the technical building systems. I now realize it's in the name twice, which are the compressed air systems, the heat production, anything that converts energy into the energy media needed in the company itself. And we look at auxiliary systems, which can just be transportation belts that kind of stuff. And then we have the energy and media systems, so looking at the energy flows into the company itself. The methodology itself is separated into 3 phases. The first phase is essentially just looking at the overall potential. The second one is tries to narrow it down into a feasible potential, and then the last phase is looks at the implementation, so tries to maximize and optimize the implementation of the identified energy flexibility measures. So when we try to collect the entire potential in the phase 1, there are certain steps we have to look or we have to carry out to make sure that we look at everything. In the beginning, I said this approach was a systematic approach for identification. So we start with, so we try to look at all the energy or all the relevant systems in the factory to catalog the entirety of the energy flexibility measures. So we usually do a factory visit, so we can see the systems where they are located. We do a very extensive data collection, and then we use all that data we collected. So we make sure we looked at all relevant systems in both those steps. Then we start the energy consumption analysis and the identification of the measures. And at the end of this phase, we have the entire energy flexibility potential. Usually that is about somewhere between 10 or 20% of the entire energy demand of a company. And then the second phase, we have to look at the energy flexibility potential and try to narrow it down into the feasible potential. So we do a technical assessment just to make sure that the technical requirements are met. This can be on the one side regarding the feasibility from the factory control system, but on the other side also looking at the industrial flexibility goals. So sometimes the flexibility is not high enough to produce or to pursue a certain goal. Then we look at the economic assessment. That's very straightforward. So the projected annual net revenue when utilizing this flexibility, but also a risk assessment. So what is the risk of utilizing this energy flexibility potential when on the manufacturing process, because a process interruption would be we try to circumvent that by doing this risk assessment. And then in the end, we have the feasible energy flexibility potential. And then we go into the third phase, which is very short. It's essentially just looking at the possibility of combination between energy flexibility measures, and then doing a prioritization, which is more for the strategy of the company when looking at the implementation of this of the identified measures. I also brought in this slide. I think there was a question about whether the slides will be uploaded, so I included this. My slides, I'm fine with them being uploaded and shared with the participants. So here's just a small overview of the possible flexibility measures. So we have the organizational measures. I'm not going to go too deep into it, but organizational measures are just essentially they just require decision by the factory personnel, while technical measures would require some sort of investment into a retrofit or new energy systems as well. So now I'm going to show 2 best practices. I have to hurry up. I see I only have 1 minute. So as I said earlier, peak shaving is a very important topic, very much pursued at the moment. And as we can see here, this is a company that produces injection molding pieces, and they have a very significant peak in the morning between 5 and 6 a.m. You can see this in the profile ID number 4, and it's usually on Monday when they start up their machines. And through this data analysis, we could identify this and look at the potential measures to circumvent this. And one potential solution to this was just adjusting the production start. So they had a lot of those machines, so they can just start those machines after each other. So the peak power in the beginning doesn't overlap together, and they can save a lot of money this way. Another best practice is the maximization of PV. So this company in this case had a PV plant on the roof, and in the summer months, you can see this highlighted in the red bar with the number 1. They usually produce with one shift only, and that shift usually started at around 5 to 6 a.m. in the morning. But actually, when we look outside at 5 or 6 a.m. in the morning, even in summer months, the sun is not really shining that much. So just by moving their shift times to later into the day, they were able to get a lot of more of their energy supplied through their PV system. So this is another way that energy flexibility can be used to improve the energetic, but also the financial side of the factory as well. And with that, I thank you very much for your attention. And I'm not sure if we can do any more questions, but in case we can't, here's my email address, and feel free to contact me after this webinar. So thank you very much. With that, I think I give back to the IAEE, I believe.
Thank you very much. There's not actually a strict cutoff at 11 o'clock. So if you would like to answer a question or two, you may. Otherwise, I'm happy to wrap things up. It's up to you.
Okay, I can see there's one question in the Q&A from Christian. Is there a minimal amount of energy consumed where it makes sense to start with flexibility? There is not a minimal amount of energy, but we can usually say about 10% is probably a good value. 10% of the energy consumed is or will be able to be what we can use for energy flexibility. And then there's a certain cutoff, sometimes like it's between, I would say, around 200 to 500 kilowatts, where a lot of those flexibility goals are not feasible anymore. So that would probably be my answer. It's probably around like 1 or 2 megawatts is where I would say about 1 megawatt of energy consumption would be a minimum value. But yeah, you cannot say this so strictly.
You also have a comment regarding Marcel Boitois.
I think this is towards Nicholas.
Oh, yes, Nicholas.
Niklas. So, but I think we had a side discussion on taxes. So I think this was more a comment, I would interpret that, right?
Okay. Well, IAEE would like to thank all of our distinguished panelists for an outstanding webinar. This webinar will be available on IAEE's website for future download. Additionally, if the speakers, if you would like to provide me with your slides, I'll be happy to upload those as well. If you're not a member of IAEE, we encourage you to join by visiting iaee.org. We thank you for attending, and I officially close this webinar.
Thank you, everyone.
Thank you. Thank you very much.
Thank you.